Hello there, and welcome to Desire Sleep Stories. Tonight, we are gently turning our attention inward to something that has been with you from the very first moments of your existence, something that continues its quiet, steady work, even as you settle here in this peaceful space, perhaps with the soft weight of a blanket around you and the room growing dimmer around the edges of your awareness. We are exploring the most relaxing facts about your heart and the gentle rhythm of life to fall asleep to. This is not a hurried lesson or a list of quick points to remember. Instead, allow these words to unfold slowly, like the natural ebb and flow of a calm evening tide, carrying you deeper into relaxation with each breath you take. Your heart has been beating since early in your development, and it does so now, right beneath your chest, in a rhythm that invites you to slow down, to notice, and to let go. We will move through this exploration with care, dwelling on each detail so that the science itself becomes a soothing companion, helping your mind unwind and your body sink further into rest. Let us begin at the very start, with how your heart first came to be, in those early weeks when your entire being was forming in the most protected environment imaginable. Around the 22nd day after conception, long before you had eyes or ears or limbs taking shape, a remarkable event occurred within the cluster of cells that would become you. 2 tubes of tissue, formed from a special layer called the splanchnic mesoderm, fused together in the midline of the developing embryo. This fusion created a single, primitive heart tube, a simple structure that began to pulse almost immediately. By day 22 or 23, that first heartbeat happened. A spontaneous contraction driven by specialized cells that had already differentiated into cardiac muscle. At this stage, the tube was straight and uncomplicated, with regions that would later become the chambers and outflow tracts, but already it was moving fluid, early blood precursors, in a looping pattern that established the basic direction of circulation. The heart tube looped to the right in a gentle C shape around days 23 to 28, a process guided by molecular signals and the addition of cells from what are known as the first and second heart fields. These fields contributed cells that helped form the future left ventricle from the first field and parts of the right ventricle and outflow tract from the second. By the end of the 4th week, the tube had begun to form distinct swellings, the truncus arteriosus at the top, followed by the bulbus cordis, the primitive ventricle, the primitive atrium, and the sinus venosus at the inflow end. These regions would remodel into the 4-chambered heart you carry today. As the weeks progressed, internal walls began to grow, dividing the single tube into separate pathways for oxygenated and deoxygenated blood. Septa, or dividing walls, formed between the atria and ventricles starting around day 28. The atrial septum grew from the roof of the common atrium downward, leaving a small opening called the foramen oval that allowed blood to bypass the developing lungs in the fetus, since oxygen came from the placenta rather than breathing air. This opening would close naturally after birth when the pressure in the left side of the heart increased. The ventricular septum formed from the floor upward, meeting the atrial septum to create the complete separation. Valves began to develop from endocardial cushions, swellings of tissue that formed the tricuspid valve on the right side between the right atrium and right ventricle, and the mitral valve on the left between the left atrium and left ventricle. Outflow valves, the pulmonary on the right and aortic on the left, took shape from ridges in the truncus arteriosus, which itself divided into the pulmonary artery and aorta. By the end of the 8th week, the heart had taken on its 4-chambered form, though still tiny, about the size of a small pea, and beating at a rate of around 140 to 150 times per minute to support the rapid growth happening all around it. This early development happened with remarkable precision, and even in those first months, the heart was already responding to the body's needs, adjusting its rhythm as the embryo grew from a few millimeters to several centimeters long. It is comforting to reflect on this, is it not, how your heart has been reliable from the beginning, a steady companion through every stage of life since then. Neural crest cells also played a supporting role in forming parts of the outflow tract separation, ensuring the pulmonary and aortic channels aligned properly, while the endocardial cushions fused centrally to help complete the partitions and contribute to the valve structures, all unfolding in a coordinated sequence that typically reaches completion by the 9th week. Now, as we rest here together, let us shift our focus to the heart you have today, nestled quietly in the center of your chest, slightly to the left, protected by the ribcage and surrounded by a thin, double-layered sac called the pericardium. This sac contains a small amount of fluid that allows the heart to move smoothly with each beat, reducing friction against the lungs and chest wall. The heart itself is about the size of your closed fist, weighing roughly 250 to 350 grams in an average adult, though it can vary based on body size and fitness level. Its outer layer, the epicardium, is a thin, protective covering. Beneath that lies the thickest part, the myocardium, made up of specialized cardiac muscle cells, or cardiomyocytes, which are striated like skeletal muscle but connected by intercalated discs that allow them to contract in unison as a single functional unit. These cells are rich in mitochondria, tiny energy-producing structures that give the heart the constant supply of adenosine triphosphate it needs to keep working without tiring, even during sleep, when your body is at its most relaxed. The innermost layer, the endocardium, lines the chambers and valves with a smooth surface that prevents blood from clotting as it flows through. Your heart has 4 chambers arranged in 2 pairs. The upper 2 are the right and left atria, smaller chambers that act as receiving rooms for blood returning from the body and lungs. The lower 2 are the right and left ventricles, larger and more muscular, because they do the heavier work of pumping blood outward. A thick wall called the septum divides the right side from the left, ensuring that oxygenated and deoxygenated blood do not mix. 4 valves keep the flow moving in one direction only, opening and closing with each heartbeat in a precise sequence that produces the familiar lub-dub sound you might notice if you place a hand gently on your chest right now. The tricuspid valve, with 3 cusps, sits between the right atrium and right ventricle. The mitral valve, sometimes called the bicuspid because of its 2 cusps, is between the left atrium and left ventricle. On the outflow side, the pulmonary valve guards the exit to the pulmonary artery from the right ventricle, and the aortic valve protects the entrance to the aorta from the left ventricle. These valves are supported by chordae tendineae, thin cords anchored to papillary muscles in the ventricles, which prevent the valve flaps from inverting under pressure. The tricuspid has 3 leaflets anchored by 3 papillary muscles, while the mitral has 2 leaflets with 2 papillary muscles. The semilunar valves each have 3 cusps that open passively with pressure and close with the help of eddy currents in the sinuses. Let us linger here for a while on the way blood moves through these chambers, because understanding this gentle circulation can itself feel like a meditative practice, a reminder of the quiet efficiency happening inside you, even as your breathing slows and your thoughts soften. deoxygenated blood, carrying carbon dioxide from the tissues, returns to the heart through two large veins. The superior vena cava brings blood from the head, neck, arms, and upper chest, while the inferior vena cava collects it from the lower body, including the legs and abdomen. This blood enters the right atrium, a chamber that relaxes to fill like a soft reservoir. When the right atrium contracts, it pushes the blood through the open tricuspid valve into the right ventricle. The right ventricle then contracts more forcefully, closing the tricuspid valve to prevent backflow and opening the pulmonary valve to send the blood into the pulmonary artery, which splits into left and right branches leading to the lungs. In the lungs, within tiny capillaries surrounding the alveoli, carbon dioxide is released and oxygen is absorbed, turning the blood a brighter red. This freshly oxygenated blood returns to the heart via 4 pulmonary veins, 2 from each lung, entering the left atrium. From there, it passes through the mitral valve into the left ventricle, the strongest chamber, whose thick walls allow it to pump with enough pressure to send blood throughout the entire body. When the left ventricle contracts, the mitral valve closes, the aortic valve opens, and blood surges into the aorta, the largest artery, which arches upward and then descends to branch into smaller arteries, supplying every organ and tissue. This entire cycle, known as the cardiac cycle, takes about 0.8 of a second at a resting heart rate of around 70 beats per minute. It consists of 2 main phases: systole, when the ventricles contract to eject blood, and diastole, when they relax and refill. During diastole, which is longer at rest and especially noticeable when you are calm like this, the heart muscle receives its own oxygenated blood through the coronary arteries that branch off the aorta just above the aortic valve. The left coronary artery divides into the left anterior, descending and circumflex branches, supplying the front and left side of the heart. The right coronary artery curves around to nourish the right side and the back. These arteries feed into a network of smaller vessels and capillaries within the myocardium, delivering oxygen and nutrients directly to the hard-working cardiac cells before the blood drains back through coronary veins into the right atrium via the coronary sinus. It is a self-sustaining loop, one that continues even when you are deeply asleep, adjusting subtly to your body's lower demands at night. The left anterior descending supplies much of the front of the left ventricle and septum. The circumflex wraps to the lateral and sometimes posterior areas, and the right coronary typically feeds the right ventricle and nodes, with natural variations among individuals and some collateral pathways providing backup in health. Now, what powers this rhythmic contraction? It is the heart's own electrical conduction system, a network of specialized cells that generate and conduct impulses without needing constant signals from the brain, though the brain and nervous system can influence the rate. The process begins in the sinoatrial node, a small cluster of pacemaker cells high in the wall of the right atrium. These cells spontaneously depolarize or fire an electrical signal about 60 to 100 times per minute in a healthy adult at rest, setting the pace for the whole heart. The signal spreads rapidly through the atrial muscle, causing both atria to contract almost simultaneously and push blood downward. It then reaches the atrioventricular node, located low in the right atrium near the septum, where it pauses for about 1/10 of a second. This brief delay gives the ventricles time to finish filling completely before they contract. From the atrioventricular node, the impulse travels down the bundle of His, a pathway that splits into left and right bundle branches running along the septum. These branches further divide into a network of Purkinje fibers that spread throughout the ventricular walls, ensuring that the contraction starts at the bottom of the ventricles and moves upward, squeezing blood efficiently out through the outflow tracts. This coordinated electrical wave produces the heartbeat you feel as a gentle thump against your chest, reliable and unhurried, especially now as you allow your body to settle deeper into the surface beneath you. The sinoatrial node is modulated by sympathetic nerves that can accelerate it, and parasympathetic fibers from the vagus nerve that slow it with acetylcholine during rest, while the atrioventricular node serves as a gatekeeper to protect the ventricles from overly rapid signals. As we continue this slow journey through the facts, consider how this rhythm connects to the broader patterns of life around you and within you. Your heart rate is not fixed. It varies naturally from moment to moment, a phenomenon called heart rate variability, or HRV, which reflects the healthy interplay between your sympathetic and parasympathetic nervous systems. Higher HRV, with more subtle fluctuations in the time between beats, is associated with greater adaptability and a calmer state. One of the most direct ways to influence this variability is through your breathing. When you breathe slowly and deeply, especially with a longer exhalation than inhalation, the vagus nerve, which runs from the brainstem to the heart and other organs, carries signals that enhance parasympathetic activity. This promotes relaxation, slowing the heart rate slightly and increasing the intervals between beats in a smooth, wave-like pattern. Practices like resonance breathing, around 5 to 6 breaths per minute, can measurably boost HRV, supporting emotional balance and a sense of inner calm. Right now, as you listen, you might notice your own breath becoming more even, perhaps inhaling gently for a count of 4 and exhaling for 6 or 7, allowing that natural coherence between breath and heartbeat to deepen your rest. Resonance frequency breathing, often near 6 breaths per minute or about 0.1 Hz, synchronizes with the baroreflex, amplifying low-frequency heart rate variability oscillations for greater coherence, and studies show it can enhance positive mood and adaptability when practiced regularly. Your heart's rhythm also follows larger daily cycles tied to your circadian rhythm, the internal 24-hour clock regulated by the suprachiasmatic nucleus in the hypothalamus. Heart rate and blood pressure tend to be lower at night during sleep, dipping to their lowest in the early morning hours, before gradually rising as you approach waking. This pattern helps conserve energy when the body is repairing and restoring itself. During non-rapid eye movement sleep, particularly the deeper stages, parasympathetic tone dominates, slowing the heart and allowing the myocardium to rest more fully. Even in rapid eye movement sleep, when dreaming occurs, the heart may show brief accelerations, but overall the nighttime hours provide a protective window for cardiovascular recovery. Disruptions to this rhythm, such as irregular sleep schedules, can affect how the heart functions, underscoring how aligning your daily life with natural light-dark cycles supports that gentle internal beat. Let us return once more to the cellular level for a deeper appreciation of what keeps your heart going. Each cardiomyocyte is packed with myofibrils, the contractile elements made of actin and myosin proteins that slide past each other during contraction, powered by calcium ions released in response to the electrical signal. The high density of mitochondria, sometimes making up 40% of the cell volume, ensures a steady supply of energy even under varying loads. These cells are connected not only electrically but also mechanically, forming a syncytium that contracts as one. Over a lifetime, your heart will beat approximately 2.5 to 3 billion times, pumping enough blood to fill a small swimming pool each day. Yet it does so with remarkable endurance because of built-in repair mechanisms and the constant renewal of its energy systems. The average resting heart rate for an adult is between 60 and 100 beats per minute, but well-conditioned individuals may have rates as low as 40 or 50, reflecting an efficient, relaxed cardiovascular system that works less hard to achieve the same output. At rest, the heart pumps about 5 to 6 litres of blood per minute, with a stroke volume around 70 millilitres per beat. To expand our understanding further, it is worth considering how the heart's structure and function have been understood through careful observation over time. In the 17th century, William Harvey demonstrated through experiments on animals and human cadavers that blood circulates in a closed loop, pumped by the heart rather than being constantly produced and consumed as earlier ideas suggested. He calculated the volume of blood ejected with each beat and showed that the heart's output far exceeded what the body could produce anew, proving the circulatory pathway. This foundational insight built on earlier anatomical descriptions from physicians like Andreas Vesalius, who mapped the chambers and vessels with increasing precision. Harvey observed that the active phase of the heartbeat decreases the heart's volume as it expels blood, and through ligature experiments on arms and animals, he showed valves direct flow toward the heart in veins. His quantitative estimates revealed that the heart moves far more blood per hour than the body could manufacture or consume, leading him to conclude circulation must occur in a closed system, with blood returning via veins after passing through tissues. Today, we know the details down to the molecular signals that guide valve formation and chamber separation during development, all verified through modern imaging and genetic studies. Your heart also maintains connections with the brain that go both ways, a bidirectional dialogue that influences how you feel and how your body responds. The heart sends more signals to the brain than the brain sends to the heart, primarily through the vagus nerve and other pathways, affecting areas involved in emotion, decision-making, and stress response. When the heart is in a coherent rhythm with smooth, ordered beat-to-beat changes, it can promote clearer thinking and a greater sense of emotional stability. Positive states like gratitude or calm can enhance this coherence, while the heart's baroreceptors, pressure sensors in the arteries, feed information back that helps regulate blood pressure and heart rate. This mind-heart interplay is why moments of relaxation, like the one you are in now, can feel so restorative. The signals encourage the whole system to settle into harmony. The vagus nerve carries sensory information from the heart to the brainstem and hypothalamus, while efferent signals modulate rate and force, creating an ongoing conversation that supports balance. Let us explore the journey of a single red blood cell to bring this circulation even more vividly to life in your imagination. Imagine one red blood cell, a flexible disc shape about 7 micrometers across, carrying oxygen bound to hemoglobin inside it. It enters the right atrium from the vena cava, dark with carbon dioxide. Pushed gently into the right ventricle, it is then propelled into the pulmonary artery, traveling to the lungs where it squeezes through capillaries so narrow it must deform slightly. There, in the thin walls of the alveoli, it releases carbon dioxide and picks up fresh oxygen, brightening to a vivid red. Returning via the pulmonary veins to the left atrium and then the left ventricle, it is ejected with force into the aorta. From there, It branches into arteries that narrow into arterioles, and finally capillaries in, say, a fingertip or a muscle in your leg. It delivers oxygen, picks up waste, and begins the return trip through venules and veins, eventually completing the loop back to the heart. This happens thousands of times per minute, every cell in your body relying on this steady supply. The total length of all blood vessels in an adult is estimated at around 60,000 miles, enough to circle the Earth more than twice, yet the heart manages the flow with quiet precision, adjusting based on needs like digestion after a meal or cooling during warmth. After leaving the left ventricle, blood first supplies the heart itself via coronaries, then reaches the brain through carotids, the liver and kidneys via dedicated branches, and every tissue through a vast branching network that returns via merging veins to the vena cavae in under a minute at rest. As you breathe slowly here, perhaps feeling the gentle rise and fall of your chest, remember that each inhalation brings oxygen that will soon reach your heart muscle itself through those coronary vessels. Each exhalation helps shift the balance toward relaxation, increasing that vagal tone we spoke of earlier. Research shows that even a few minutes of slow breathing can elevate measures of heart rate variability, such as the root mean square of successive differences or the standard deviation of intervals between beats, markers of a resilient autonomic nervous system. In one approach called resonance breathing, aiming for about 5.5 to 6 breaths per minute maximizes the amplitude of these fluctuations, creating a state where the cardiovascular system operates with optimal efficiency and calm. We can also appreciate the heart's role in the broader context of life's rhythms by noting how similar patterns appear across scales. The heart's beat echoes in the way tides rise and fall or seasons change, though of course these are separate phenomena. The parallel lies in the reliability of natural cycles that sustain existence. In humans, the average adult heart pumps about 5 litres of blood per minute at rest, increasing during activity but returning to baseline during sleep, where the rate might drop to 50 or 60 beats per minute in deep rest. This nightly slowdown allows the body to prioritize repair, with growth hormone and other restorative processes peaking in the early hours. To add another layer to our exploration, consider the layers of the heart wall once more, but from the perspective of how they adapt over time. The myocardium can hypertrophy or thicken in response to sustained demands like regular exercise, making the heart more efficient rather than strained. Cardiac cells themselves have limited ability to divide after birth, but the heart maintains function through hypertrophy of existing cells and support from surrounding connective tissue and blood vessels. The endocardium remains smooth to minimize turbulence, preventing unnecessary wear. The pericardium, with its fibrous outer layer and serous inner layers, anchors the heart while permitting movement, a balance that protects without restricting. The pericardial fluid, typically 15 to 50 milliliters, lubricates the surface, allowing the heart's slight twisting motion with each beat. Let us dwell on the sounds of the heart for a moment, those subtle lub-dub tones produced by the valves closing. The first sound, S1 or lub, comes from the closure of the mitral and tricuspid valves at the start of ventricular systole. The second, S2 or dub, arises from the aortic and pulmonary valves snapping shut at the end of systole. In some people, especially during relaxation or in certain positions, a third sound, S3, can be heard in early diastole as blood rushes into the ventricles, a normal finding in younger or athletic individuals, indicating good compliance of the heart muscle. These sounds, if you were to listen with a stethoscope, reveal the precision of the system working in harmony. Expanding on the electrical system once more, the sinoatrial node's rate is influenced by ion channels, including the funny current that allows gradual depolarization. The bundle of His and Purkinje fibers conduct rapidly to synchronize ventricular contraction from apex upward. The blood itself deserves a gentle reflection here too. Plasma, the liquid portion, carries nutrients, hormones, and waste. Red blood cells, produced in bone marrow at a rate of about 2 million per second, live around 120 days before being recycled. White blood cells patrol for immune needs, and platelets help with clotting if needed. All of this travels in a volume of about 5 litres in an average adult, recirculating fully every minute or so at rest. As we near a natural pause in our journey, allow these facts to settle like soft leaves drifting down in a quiet forest. Your heart has been with you through every joy and challenge, adjusting its rhythm to support you without demand for attention. In moments like this, when you choose to rest, it responds by easing into a more tranquil pace, its variability increasing as a sign of health and adaptability. The gentle rhythm of life continues, linking your breath, your thoughts, and this central pump in a seamless flow that invites deeper sleep. We can revisit the embryonic story with fresh eyes now that we know the adult form. Those early pacemaker cells in the primitive tube were the precursors to today's sinoatrial node, already establishing autonomy so that the heart could beat before the nervous system fully connected. The looping process ensured the proper alignment for efficient separation of pulmonary and systemic circuits, a 4-chamber design that supports high metabolic demands in warm-blooded creatures. In contrast to simpler 2-chamber hearts in some aquatic animals or 3-chambered ones in amphibians, the human version fully separates oxygenated and deoxygenated blood, maximizing efficiency for sustained activity and rest alike, though we focus here on the human experience as it relates to your own body. Septation involved complex fusions completed mostly by week 8, with the foramen oval remaining open until birth pressure shifted. History offers another angle for appreciation. Long before modern imaging, ancient physicians observed the pulse and inferred the heart's central role, but it was Harvey's quantitative approach in the 1600s that clarified the circulation as a closed system driven by the heart's pump action. He estimated stroke volume and cardiac output by measuring how much blood the heart ejected per beat multiplied by the rate, showing it matched the volume returning. This laid the groundwork for today's understanding of pressures, flows, and adaptations. His ligature tests on veins confirmed unidirectional flow toward the heart, disproving earlier notions of constant new blood production. On the cellular front, cardiomyocytes are unique in their endurance. Unlike many other muscle types, they rely heavily on aerobic metabolism, using fatty acids and glucose to fuel the constant contractions. Their intercalated discs contain gap junctions for ion flow and dermosomes for mechanical strength, ensuring that a wave of contraction propagates smoothly without tearing the tissue. Breathing techniques that enhance heart rate variability have been studied extensively. For instance, slow-paced breathing increases high-frequency components of HRV, reflecting stronger vagal influence. Resonance frequency breathing, personalized but often around 6 breaths per minute, aligns with the natural baroreflex rhythm, amplifying the oscillations in blood pressure and heart rate for greater coherence. This state is linked to improved mood, reduced perceived stress, and better cognitive function, all while the body rests. Long-term practice can sustain higher baseline HRV, supporting resilience. Your circadian influences extend to gene expression in the heart itself. Clock genes regulate daily patterns in ion channels and metabolic enzymes, timing when the heart is most resilient or vulnerable. Morning hours see a natural uptick in blood pressure and platelet activity, which is why certain events follow diurnal patterns, though nighttime remains a period of relative cardiovascular quietude during sleep. To elaborate on coronary circulation once more, flow peaks during diastole when the relaxed muscle does not compress the vessels, making adequate filling time at slower rates important for the heart's own nourishment. As your eyelids grow heavier and your breathing deepens further, know that these facts are not meant to engage your analytical mind, but to cradle it in wonder and calm. The heart's rhythm is the gentle drumbeat of life, syncing with the world's natural pulses in ways that science continues to reveal. Whether it is the way slow exhalations lengthen the intervals between beats, or how the embryonic heart's first pulse set the stage for decades of faithful service, every detail points to a system designed for quiet reliability. Let us circle back to the valves with added detail. The aortic valve's cusps are positioned relative to the coronary openings, and closure is aided by natural fluid dynamics in the sinuses. The pericardial fluid allows the heart to twist slightly with each beat, a ringing motion that aids efficient ejection. The fibrous pericardium anchors to the diaphragm and vessels, preventing overexpansion. In terms of numbers, the left ventricle generates pressures up to 120 millimeters of mercury during systole, enough to propel blood to the toes and back. The right side operates at lower pressures, around 25 millimeters of mercury, suited to the shorter pulmonary circuit. Cardiac output at rest averages 5 to 6 liters per minute, calculated as stroke volume times heart rate. HRV metrics include SDNN, often around 50 to 100 milliseconds in healthy adults at rest, higher with good vagal tone. RMSSD focuses on short-term changes sensitive to parasympathetic activity. During meditation or slow breathing, these can rise significantly. The heart generates its own electrical field, detectable on electrocardiograms, with P wave for atrial depolarization, QRS for ventricular, and T for repolarization. Red blood cells lack nuclei to maximize space for hemoglobin, each carrying about 270 million molecules. They deform to pass through capillaries, recovering shape afterward. This level of detail across anatomy, physiology, development, history, cellular function, neural connections, breathing influences, and circadian patterns provides a rich, immersive narrative. The heart continues its work in perfect harmony with the life you are living. Tonight, as sleep approaches, let its gentle rhythm be your guide, a constant, reassuring presence that has carried you through every moment and will continue to do so. Rest now, allowing the words to fade into the background like a soft lullaby, your breath slow, your body heavy, your mind at peace. The most relaxing facts about your heart remind us that life itself moves in cycles of giving and receiving, pumping forward with quiet strength. Good night and sleep deeply.